Hi girls, it's me again, giving you a lesson on how to use your data sheet. And in today's lesson, we're going to be focusing on how to use the standard reduction potentials. So before you start, pause the video and go and get your data sheet because you're going to need it for this video because you're going to be writing lots and lots of information on your data sheet. Just a moment to recap. Remember, a redox reaction consists of two half reactions, oxidation and reduction. Now, the oxidation reaction always involves losing electrons, and the reduction reaction involves gaining electrons. Now, these two processes are simultaneous and interdependent. Now, what that means is that you cannot have oxidation without reduction or reduction without oxidation. Now, a potential difference occurs between each half reaction, and this is sometimes called the electromotive force or EMF, and it's actually more commonly referred to as a voltage. And this happens because it's energetically favourable for the electrons to be in a lower energy state. So we often want to have an idea of which half reaction has the lower energy state. But to obtain these, we have to couple a particular half reaction with another half reaction to be able to measure it. So we actually couple them to what's called a reference cell. Now, the reference cell that we have chosen is the hydrogen ion hydrogen gas reference cell. It consists of a platinum electrode, and we usually have a glass tube over it to keep the hydrogen gas in contact with the platinum. And this reference cell is coupled to another half cell or half reaction that you're interested in to obtain a voltage value. Now, because it's a reference cell, we have decided that the E0 value for this reference cell has been arbitrarily given 0 volts. So it's 0 exactly. Every other half cell has been coupled to the reference cell in order to get the E0 value. So what you can see in this diagram here is this one here is the reference cell. And the reference cell has been coupled to another half cell. So this is one half reaction, and it's been coupled to another half reaction. And in this particular case, the half reaction it's coupled to here is zinc going to zinc ions. So we can measure the electromotive force of the zinc going to the zinc ions because we've coupled it to a reference cell. Now, all reduction potentials are measured under standard conditions, and the standard conditions are 1 molar solutions, 100 kilopascals for gases, and they're always done at 25 degrees Celsius, which is considered to be a standard laboratory temperature. If any of these conditions are varied, then the actual E0 or voltage will be different. So the only time it's exactly what it is on the data sheet is when these conditions are applied. Now this is the standard reduction potential tables, and I want you to draw on your own table what we're doing here so that you've got something to refer back to. The first thing you'll notice is it tells you very clearly it's at 25 degrees Celsius. So these values are only valid for that temperature, 1 molar solutions, and for gases 100 kilopascals for gases. Anything from that varies from those conditions, you'll get a different result. Now, when we read left to right, which is as it's written, it becomes a reduction half equation. So for the first one, it's fluorine plus 2 electrons goes to 2 fluoride ions. Now, because I'm writing as a reduction half equation, I've written it as single arrow reduction. So the E0 for reduction, reading off the data sheet, is positive 2.89 volts. Now, what does this number tells us is that fluorine accepting electrons is really likely to happen. It's got a high positive voltage. So that means that fluorine is a strong oxidizing agent because it's really easy to reduce. When, however, you get to the bottom here, with potassium ions going to potassium, you see the value is negative 2.94. This means it's not likely to be reduced. And that's fairly obvious because we know that potassium doesn't want to exist in nature as a metal. It wants to exist as a salt. In other words, as an ionic compound, as potassium ions. So I want you to write this on your table. Going down the table, at the top we have easy to reduce, which makes it a strong oxidizing agent. Whereas at the bottom, they're hard to reduce, which makes it a weak oxidizing agent. Now, when we go the other way, so when we're reading this table from right to left, so we're reading in the opposite direction now. What you see happens when you read from right to left is that you are actually now looking at oxidation half equations. Now, because we're going from right to left, so say we look at potassium, goes to potassium ions plus an electron. So it's an oxidation half equation. Because we've reversed the direction, we actually reverse the sign. It's the opposite sign. So the E0 for oxidation then is now positive 2.94 volts. So we have, because we're going in the opposite direction, we're reversing the sign. So that means that as you go from the bottom all the way up to the top, when we're reversing the direction, so potassium here on the right hand side is really easy to oxidize, which makes it a strong reducing agent. Now at the top, if you go from fluoride ions to fluorine gas, and this doesn't really want to happen, then you'll notice it goes, instead of being E0 for the E0 for the oxidation, then is now negative 2.89 volts. So this is telling us that it doesn't want to happen. So this is hard to oxidize. Which means it's a poor reducing agent. So using this information, we can predict the likelihood of an equation taking place. So we can predict likelihood of a reaction. You need to be able to predict the likelihood of a reaction taking place. In this particular reaction, it's a metal displacement reaction. And what we've got is a piece of copper has been put into silver nitrate solution. And you can see by the pictures how it's changing over time. The observations that you see here is the copper wire goes silver. And you can see here that we've got a silver deposit. And that silver deposit is actually metallic silver. And what we've got here is you can see that the solution goes blue. So that's telling us that there are copper ions present. And you can probably predict the reaction that's going to take place. Now, what we're going to do is we're going to look at how to use the data sheet to make the prediction and work out the electromotive force, or the EMF. So the first thing we're going to do here is record the species present. So I have copper, I have silver ions, I have nitrate ions, and I have water. Now the nitrate ions are a spectator. This is because the nitrogen's already in a high oxidation state. In this particular case, the water will not participate, and we'll look at why. So this method that we're going to use to determine the likelihood of reaction, I'm going to call the power of the fingers. Because your fingers here are really, really important in determining whether it's going to take place or not. So, to start, you put your left finger right at the top, right here, and you only looking at the left hand side here. Do not look at the right hand side at all, and you move your finger downwards until you find the first species on this list. So if I follow my finger downwards, and this is what I'm doing with my finger, I'm going down, 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 down. The first thing I encounter is the silver ion. This means the silver ion is the strongest oxidizing agent present. If I went further downwards, I would see that water is also present, but it is not a strong oxidizing agent. Have a look at the differences. Our silver ions going to silver has an E0 for reduction of positive 0.8 volts, whereas water going to hydrogen gas has an E0 for reduction of negative 0.83. So that means the silver ions reducing is much more likely to happen because it's a stronger oxidizing agent than water. So we're going to write down now that our silver ions plus an electron goes to silver. Its E0 for reduction is equal to positive 0.80 volts. Now, we've left our finger on that half reaction. We've left it just here. Now what we're going to do is we're going to find the half reaction for oxidation. So using the power of your right hand finger now, you are starting at the bottom. We always start at the strongest reducing agent, which is potassium. So we are now looking from right to left. Because we're looking from right to left, we reverse the numbers. So putting your finger on and moving upwards, the strongest reducing agent that you encounter is this one, copper. So that is going to be the most likely reaction to take place. If you go further up, you'll see water. But going in the opposite directions, let's have a look at the E0 for oxidation. Copper's is negative 0.34 and water is negative 1.23. So the one most likely to take place here is your copper. So this is the strongest reducing agent we've got in this system. So let's write the half equation. Copper goes to copper 2 plus 2 electrons. The E0 for oxidation is equal to negative 0.34 volts. So now we've got an oxidation half reaction and a reduction half reaction. So we're going to put them together to get the overall reaction and see whether or not this reaction occurs. Now we already know it happens because we've seen it, but I'll show you what happens. So in order to add these two half equations together, you're going to have to multiply this one by 2. Now whatever you do, do not touch this number. You are not allowed to multiply it. It stays the same no matter what. It's always positive 0.8 volts. I don't care that you've multiplied this by 2. Do not touch this number. So you're going to end up with 2 silver ions plus copper goes to copper 2 plus 2 silver. Now to work out the E0 for the cell, and that's what it's called when you put the two together, you add the two values together. So plus 0.8 add negative 0.34 becomes positive 0.46 volts. Now because this is a positive number, it will be a spontaneous reaction. If it came out to a negative number, it would be a non-spontaneous reaction. So in other words, a no reaction. So you would have to force it to occur otherwise. So, but using your fingers, what you will have noticed with your fingers is if the left finger is above the right finger, it's a spontaneous reaction. If the right finger is above the left finger, it'll always come out to a negative number and it's non-spontaneous. So your fingers can give you a lot of information about whether or not the reaction is going to take place. So let's look at another example. In this example, what we have is acidified potassium permanganate. Remember, acidified means it's got hydrogen ions present. And we're going to add it to iron 2 sulfate solution. Now, the sulfate is in a very high oxidation number, the sulfur. So this is only a spectator. Now, what you can see happening here, here's our potassium permanganate. It's a very deep purple solution. Here's our iron 2, which is very pale green, and over time it goes to a reddy colour. That's because you're making iron 3 solution. So let's look at how. In this particular reaction, we've got iron 2 ions, we've got sulfate ions, which are a spectator, we've got potassium ions, which are also a spectator. We've got permanganate ions and water, which is pretty much a spectator as well, and hydrogen ions. So, using the power of the fingers, you always start at the top for the strongest oxidizing agent and move downwards. And what you encounter first is the permanganate. That is the strongest oxidizing agent. So we write down that's our likely reaction. And E0 for reduction is positive 1.51 volts. Now, using the power of the right finger now, you start at the strongest reducing agent and go upwards. So the strongest reducing agent, as you move upwards, oh look, here's iron, but it's not that iron because we don't have solid iron. We keep going upwards until we encounter iron 2, which is here. It has to be on the right hand side. So for this, iron 2 goes to iron 3 plus an electron. The E0 for oxidation is going to be negative 0.77 volts. So now we put them together. Now to put them together, you're going to have to multiply this by 5 because of the 5. So this becomes permanganate plus 8 hydrogen ions plus 5 Fe2 ions goes to manganese ions plus 4 water plus 5 Fe3 plus ions. Now the E0 for the cell is just adding the numbers together. You are not allowed to multiply this by 5. Do not touch the E0 value. So the E0 value for this particular cell is positive 0.74 volts. So this reaction is likely to occur, and you'll notice your fingers left above right, positive reaction. Now remember, these numbers give you an idea of the likelihood of reaction. It doesn't guarantee reaction because other factors such as rate of reaction, which is influenced by activation energy, can also contribute to whether or not it's likely to occur. You need to try some yourself. Go to the OneNote Redox Balancing Displacement Reactions, and I've made a video of me doing the questions so that you can check out your answers.